What if everything we think we know about reality is just a tiny fragment of a much grander story? Picture our universe not as a solitary island in the void, but as one of countless cosmic bubbles, each with its own unique laws of physics, its own history, its own destiny. Some of these universes might be almost indistinguishable from our own, while others could be so alien that our minds can't even begin to comprehend them. And sometimes, just sometimes, these separate realities might brush up against one another, leaving faint but detectable traces, echoes of lost universes that whisper to us from beyond the boundaries of our own cosmic home. This isn't just the stuff of science fiction or philosophical speculation. It's a serious, cutting-edge theory in modern cosmology, one that's gaining traction among some of the brightest minds in physics. The idea that we might one day hear the reverberations of other realities colliding with our own challenges, our most fundamental assumptions about existence. It asks us to reconsider what it means to be part of a universe and whether we're truly as alone as we might appear. In this video, we're going to explore this mind-bending possibility in depth, from the scientific frameworks that make it plausible to the incredible technology that might one day allow us to detect these cosmic whispers. We'll dive into the mysteries of the multiverse, examine the anomalies in our deepest space observations that could be hints of something extraordinary, and ponder the profound implications of what it would mean to finally hear those echoes. This journey will take us to the very edge of human knowledge, where established science meets thrilling speculation, and where every new discovery has the potential to rewrite our understanding of everything. So get ready to question all you thought you knew about reality itself, because we're about to embark on an exploration that just might change how you see the cosmos and our place within it forever. To understand how we might detect these cosmic echoes, we first need to grasp the stunning idea that our entire universe may not be alone. This is the concept of the multiverse. For centuries, we've operated under the assumption that everything we can see, from the smallest particle to the most distant galaxy, is part of a single, immense, and singular cosmos. But modern physics has begun to challenge that very foundation, suggesting that what we call the universe might actually be just one page in an infinite book, or one bubble in a vast cosmic foam. This isn't a claim made lightly. It emerges from the rigorous mathematics of our most successful theories. Take inflationary cosmology, for instance. This theory, which beautifully explains the uniformity and structure of our universe, proposes a period of rapid expansion just after the Big Bang. But many versions of inflation don't have a neat stop button. Instead, they suggest that this expansion could be eternal, constantly spawning new pocket universes with potentially different properties, forever disconnected from our own. String theory, a leading candidate for a theory of everything, adds another compelling layer. To be mathematically consistent, string theory requires more dimensions than the three of space and one of time that we experience. Some solutions within string theory suggest these extra dimensions could be compacted in countless different ways, with each possible configuration giving rise to a universe with its own unique set of physical laws and constants. The number of possible universes predicted this way is almost unimaginably vast. The physicist André Linde was instrumental in developing the theory of chaotic inflation, which paints a picture of a self-reproducing, eternal multiverse, endlessly giving birth to new cosmic domains. And we can't discuss the multiverse without honoring Hugh Everett III, whose many worlds interpretation of quantum mechanics proposed that every quantum decision point causes reality to branch, creating a constantly proliferating tree of parallel universes where every possibility is realized. Now, you might be wondering why such a seemingly outlandish idea has gained serious traction in the scientific community. It's not because physicists have given up on finding a single, elegant theory for our universe. Rather, it's because the multiverse concept, for all its strangeness, potentially solves some profound puzzles. Why, for example, do the fundamental constants of nature, the strength of gravity, the mass of an electron, seem so perfectly fine-tuned to allow for the existence of stars, planets, and life? If there is only one universe, this appears to be a miraculous coincidence. But if there are countless universes, each with its own random set of rules, then it's no surprise that we find ourselves in one of the rare Goldilocks-style universes where conditions are just right. We are, in a sense, living proof of its habitability. This idea pushes the boundaries of science, blurring the line between physics and philosophy, and forces us to reconsider our place in a reality that might be far grander and more mysterious than we ever dreamed. And if these countless universes are out there, it begs a thrilling question: could they ever touch? So if our reality is just one bubble in a cosmic foam, what happens when these bubbles meet? The idea of entire universes bumping into one another sounds like the climax of a science fiction epic. But within the framework of modern cosmology, it's a serious theoretical possibility. Think of it like this: imagine you're blowing bubbles in your backyard on a windy day. Even as they all float away from you, expanding as they go, the wind can still push a few of them together. They might gently graze each other, merge into a larger, wobbling blob, or even pop against one another. Now scale that up to a cosmic level. In the eternal inflation model, new universes are constantly nucleating out of the inflating background energy, each one a separate bubble with its own distinct spacetime. While the space between these bubbles is expanding incredibly fast, often faster than the speed of light, the bubbles themselves are also growing. Under just the right conditions, if two bubbles are born sufficiently close to one another and their expansion rates align, their boundaries could make contact before the inflating space between them pulls them irrevocably apart. The mechanics of such a collision are governed by the same rules that dictate everything in the cosmos, the laws of physics, particularly general relativity. The boundary of a universe bubble isn't a physical wall. It's a region where the energy fields that define that universe transition to the state of the inflating background or to the fields of a neighboring universe. When two of these boundaries meet, it's less like two cars crashing and more like two weather fronts colliding, creating a complex storm of interacting energies. The role of dark energy is crucial here. In our universe, dark energy is causing an accelerated expansion, but in the multiverse foam, the energy landscape is varied. Some universes might have much stronger dark energy, causing them to expand so violently they never meet another. Others might have weaker or even negative dark energy, making them more susceptible to a close encounter. The curvature of space-time at the very edge of a universe would be immense, and a collision would send powerful ripples, shockwaves, propagating through the fabric of both universes involved. The potential outcomes of such an event are as fascinating as they are varied. A relatively gentle collision might leave a faint, circular imprint in the cosmic microwave background, a bruise on the sky, a relic of a long-ago encounter with another reality. This is precisely what researchers like Stephen Feeney and his team have searched for, scouring data from the Planck satellite for telltale patterns. A more violent merger could have profound consequences, perhaps even altering the very laws of physics within the collision zone. It's conceivable that a region of our universe could have slightly different fundamental constants, a stronger gravitational force, or a different speed of light, acting as a permanent scar from this cosmic trauma. In the most extreme scenarios, a collision could even spawn an entirely new cosmic structure, a bizarre hybrid region where the rules of two separate realities mix and compete. Visualizing this is a challenge, but the imagery is powerful. Picture the quiet, uniform darkness of the early universe just after the Big Bang. Suddenly, from one direction, a wall of unimaginable energy, the leading edge of another cosmos, sweeps through. It wouldn't be a wall of fire and light as we know it, but a wave of pure geometry, reconfiguring space-time itself as it passes. The universe would ring like a bell, and the echoes of that ringing might still be detectable today as subtle variations in the temperature of the ancient light that fills our sky. These events would be among the most violent and energetic since creation itself, yet their signatures would be incredibly subtle, hidden in plain sight within the faint afterglow of our own birth. Finding them requires not just powerful telescopes, but immense creativity and a willingness to look for the extraordinary in the most mundane of data. Finding evidence of something as monumental as a collision with another universe is paradoxically an exercise in searching for the most subtle and faint of whispers in a cosmic hurricane of noise. The first and most formidable challenge is simply the sheer scale involved. Any imprint left by such an event would be ancient, dating back to the universe's infancy, and stretched across billions of light years by its subsequent expansion. This means the signal we're looking for would be incredibly diluted, a ghostly pattern etched onto the oldest light we can see, the cosmic microwave background. This afterglow of the Big Bang is remarkably uniform, with temperature variations across the sky measured in mere millionths of a degree. A collision signature would be a tiny perturbation within these tiny fluctuations, a subtle circular bruise or a specific pattern of polarization that stands out from the primordial randomness. It's the ultimate needle in a haystack problem, where the haystack is the entire observable universe and the needle is potentially smaller than our ability to resolve. Our technological eyes on the sky, while incredible, have fundamental limitations that make this search even harder. Telescopes like the Planck satellite, which provided our most detailed all-sky map of the cosmic microwave background, have a finite resolution. Think of it like a digital camera. There's a limit to how small a pixel you can have, and details smaller than that pixel get blurred together. Planck's resolution is astounding, but a predicted collision signature might be even fainter or cover a smaller angular size on the sky than what its instruments can clearly distinguish. We're trying to read the faintest of handwriting from an immense distance, and our best glasses still might not be strong enough. Furthermore, these instruments must contend with a wall of foreground interference. Our own galaxy emits microwave radiation from dust and synchrotron radiation from electrons spiraling in magnetic fields. This galactic static isn't just a nuisance. It's a bright, messy veil draped over the pristine primordial signal we're desperate to see. Untangling the cosmic microwave background from this galactic pollution requires sophisticated statistical models and filters, each step introducing its own potential for error and accidentally erasing or creating a false signal. Beyond our galaxy, other astrophysical phenomena create their own confusing echoes. The gentle rumble of gravitational waves from merging black holes and neutron stars, the subtle distortions caused by the gravitational lensing of distant galaxies, and the vast cosmic voids that can slightly cool the light passing through them. All of this creates a complex symphony of background noise. A potential collision signal would be a single, faint note in this symphony, easily mistaken for a known instrument or lost in the cacophony. This is where the creativity of cosmology truly shines. Scientists don't just build better telescopes, they build better algorithms. They run millions of computer simulations, modeling what a collision would look like under different conditions, and then developing statistical techniques to search for those specific patterns in the real data. They use techniques like Bayesian inference to weigh the probability that a detected anomaly is a real signal versus just a rare statistical fluke in the Gaussian noise of the early universe. Projects like Planck have scoured its data for these exact patterns, and while a handful of curious anomalies have been flagged, areas that are slightly too cold or have unusual polarization, none have risen to the gold standard of 5 sigma significance required to claim a discovery. They remain intriguing maybes, hints that keep the search alive but fall agonizingly short of definitive proof. The history of science is littered with such tantalizing ghosts, from the pioneer anomaly to the faster-than-light neutrinos, which were eventually explained by conventional means like instrumental error or unaccounted-for physics. This immense difficulty forces a profound question. Are we not looking hard enough, or are we perhaps looking for the wrong thing entirely? So where do we even begin to look for these cosmic bruises? The most promising hunting ground is the cosmic microwave background, that faint echo of the Big Bang that permeates all of space. This ancient light is like a baby picture of our universe, and etched into its subtle temperature variations could be the scars of a traumatic encounter with another reality. One of the most famous and debated anomalies is known as the cold spot. This is a region in the constellation Eridanus that is significantly colder than the surrounding area, a large, mysterious chill on the face of the cosmos. According to our standard model of cosmology, such a large and pronounced cold region is extremely unlikely to have formed by random chance. It's a statistical outlier that has puzzled astronomers since it was first clearly mapped by the WMAP satellite and later confirmed by Planck. One provocative explanation is that this cold spot is the imprint of a collision with another universe bubble. The theory suggests that if such a collision occurred, it would have drawn energy out of that region of space through a complex interaction of gravitational fields, effectively creating a vast cosmic shadow that we now observe as a cold patch in the microwave background. But the cold spot isn't the only curious feature. Researchers also scrutinize the CMB for specific patterns in polarization, the way the light waves are oriented. A universe collision could generate a unique, swirling pattern in this polarization, known as B-mode polarization, that is distinct from the patterns created by more conventional sources like gravitational waves from inflation. Finding such a specific fingerprint would be incredibly compelling evidence. Scientists don't just stare at maps hoping something looks weird. They employ incredibly sophisticated statistical machinery. They use something called Bayesian analysis, which is a way to calculate the probability that a given anomaly is due to a collision versus just being a random fluke. They run thousands of computer simulations of the universe, both with and without collisions, to create a library of what both scenarios should look like. They then compare the real data from Planck to both sets of simulations, asking which one it resembles more. It's a cosmic game of spot the difference, played with the highest stakes imaginable. The work of researchers like Stephen Feeney at University College London has been at the forefront of this search. His team developed algorithms to scan the Planck data for specific circular patterns that would be the trademark of a bubble collision. In 2011, they published a paper suggesting they had found 4 promising candidates that were consistent with what a collision signature might look like. However, they were careful to state that these were not discoveries but merely hints that were consistent with the theory. The scientific community responded with intense scrutiny. Other groups analyzed the same data with different statistical techniques, and argued that the identified features could easily be explained by chance alignment or instrumental noise. The Planck collaboration itself later performed its own, more sensitive analysis and concluded that there was no conclusive evidence for such collisions in their data, effectively dampening the initial excitement. This back and forth is not a sign of failure, it's the very engine of science working as it should. Extraordinary claims require not just evidence, but evidence that survives every attempt to tear it apart. This ongoing debate highlights the immense challenge of this work. The potential signals are so faint that they exist right on the edge of what our instruments can detect and our statistics can confirm. A slight tweak to the analysis method or a different way of modeling foreground dust can make a tantalizing signal vanish into the noise. It forces cosmologists to be both bold in their theories and ruthlessly self-critical in their data analysis. The story of the cold spot perfectly illustrates this tension. While some teams hold out for the multiverse collision hypothesis, others have proposed more conventional, if still exotic, astrophysical explanations. One leading alternative is that the cold spot is not a sign of another universe, but a sign of a vast nothingness, a supervoid. This theory suggests that the cold spot is an enormous region of space with far fewer galaxies and clusters than average. As light travels through such a void, it can lose energy due to the changing gravitational landscape, an effect that could potentially explain the observed temperature dip. However, even this explanation has its problems, as surveys to map the galaxy distribution in that region have had mixed results, sometimes finding a void but not one large or empty enough to fully account for the coldness. The mystery endures, making it one of the most captivating unsolved puzzles in modern cosmology. While the idea of a bruise from a colliding universe is thrilling, science demands we first rule out the mundane before embracing the miraculous. The cosmic microwave background is a faint and ancient signal, and teasing out its true meaning requires us to consider every possible explanation that originates within our own familiar cosmic walls. One of the most significant hurdles is the simple, sobering reality of instrumental error. Our satellites, like Planck, are marvels of engineering, but they are not perfect. They have specific resolutions, calibration quirks, and potential systematic biases that can subtly imprint patterns on the data. A faint circular smear might not be a cosmic bruise at all, but an artifact of how the telescope scanned that particular patch of sky or how its detectors were normalized. Scientists spend years meticulously modeling and subtracting these instrumental effects, but an unknown systematic error could easily masquerade as a new physical phenomenon, a ghost in the machine mistaken for a ghost from another reality. Then there is the ever-present specter of chance. Our universe is vast, and the laws of statistics guarantee that even in a perfectly random, Gaussian distribution of temperature fluctuations, there will be outliers, regions that are unusually hot or cold simply by random luck. It's like rolling a die 1,000,000 times. You will eventually get a sequence of 20 zeros in a row, not because the die is loaded, but because you rolled it enough times for that incredibly rare event to occur. The cold spot, for all its intrigue, might be exactly that, a 1 in a million statistical fluke in the primordial lottery. The challenge for cosmologists is to calculate the precise probability of such an anomaly appearing by chance alone. If the probability is sufficiently low, say 1 in 100,000, then we start to get interested. But even then, with the entire sky to analyze, the chances of finding some unusual-looking feature are actually quite high, a problem known as the look elsewhere effect. We can't just point to one strange spot and declare victory. We have to account for the fact that we searched the entire cosmos for anything strange. Moving beyond measurement and chance, there are compelling astrophysical explanations that reside entirely within our standard model of cosmology. The leading contender for the cold spot, for instance, is the supervoid hypothesis. Imagine a region of space that is not just empty, but profoundly, unusually empty, a cosmic desert on a scale of hundreds of millions of light-years, with far fewer galaxies, gas, and dark matter than the surrounding universe. When light from the cosmic microwave background travels through such a void, it encounters a gravitational landscape that is different from the dense regions around it. According to the integrated Sachs-Wolf effect, photons of light can gain a tiny amount of energy when they fall into a gravitational well, but they lose a tiny amount when they climb out. In a slowly evolving universe dominated by dark energy, a photon climbing out of a deep void will lose more energy than it gained entering it. This net energy loss would manifest as a slight cooling of the CMB light passing through that region, which could explain the cold spot. The catch: surveys mapping the galaxies in that direction have found evidence of a void, but it doesn't appear to be nearly large or empty enough to account for the significant temperature dip we observe. This leaves the mystery open, with some scientists proposing a combination of a moderate void and a statistical fluke might be to blame. Another ever-present contaminant is our own galactic neighborhood. Our Milky Way galaxy is not a silent observer, it's a source of microwave radiation itself. Clouds of cold dust and fast-moving electrons can emit light at the same frequencies we use to observe the pristine cosmic microwave background. This foreground emission is like a dusty window we have to look through to see the distant universe. If there is an unusual, faint cloud of galactic dust or a subtle magnetic field structure in the direction of the cold spot that we haven't perfectly modeled and subtracted, it could leave a residual cold patch in the data. Cleaning this galactic foreground is one of the most complex and crucial steps in analyzing CMB data, and any imperfection in that cleaning process could potentially create an artificial anomaly where none truly exists. This rigorous process of considering alternatives is not a sign of weakness in the multiverse hypothesis. It is the very essence of scientific strength. Prominent skeptics like Princeton physicist Paul Steinhardt have been vocal critics. They argue that invoking an infinite number of unobservable universes to explain a faint anomaly in our own is a dangerous step away from empirical science. It risks becoming a theory that can explain anything but predicts nothing specific, effectively making it unfalsifiable. The mantra echoed by these scientists is the famous principle popularized by Carl Sagan: extraordinary claims require extraordinary evidence. A few statistical curiosities in exquisitely complex data, they argue, simply do not meet that high bar. This healthy skepticism is what forces proponents to sharpen their theories, to make more precise predictions, and to search for even cleaner signatures that are less susceptible to conventional explanations. It is this tension between bold speculation and rigorous doubt that drives cosmology forward, ensuring that if and when we finally do hear an echo from another reality, the evidence will be so rock solid that it will transform our understanding of existence forever. While the search for echoes in the cosmic microwave background is like looking for a fossilized imprint, gravitational waves offer us the chance to listen to the universe's dynamic symphony in real time. These ripples in the fabric of spacetime, first predicted by Einstein and spectacularly confirmed by LIGO in 2015, are caused by the most cataclysmic events in the cosmos, the mergers of black holes and neutron stars. But what if some of these ripples aren't from within our cosmos at all? If a collision with another universe occurred, it would be an event of almost unimaginable violence, a shockwave propagating through the very geometry of existence. Such an event wouldn't just leave a static bruise on the cosmic microwave background. It would set spacetime itself ringing, generating a unique gravitational wave signal that could, in theory, travel across the multiversal divide and into our detectors. The key to identifying such an extraordinary signal lies in its uniqueness. The gravitational waves we regularly detect from black hole mergers have a very specific fingerprint. They start at a low frequency, rapidly rise to a peak as the objects spiral inward, and then abruptly cease in a characteristic chirp as they merge. A wave generated by a universe collision would be utterly different. Instead of a brief chirp, it might be a long-duration, persistent hum, a monochromatic sine wave that could last for years or even centuries. This is because the source wouldn't be two compact objects orbiting each other, but a vast structural event shaking the foundations of reality itself. The frequency of this hum would be another telltale sign. It would likely exist at extremely low frequencies, far below what ground-based detectors like LIGO can hear. LIGO is like a superb microphone for the high-pitched screams of stellar mass collisions, but to hear the deep, cosmic bass notes of a universe colliding, we need a much larger instrument. This is where future projects like the Laser Interferometer Space Antenna, or LISA, come into play. Scheduled for launch in the next decade, LISA will consist of 3 spacecraft flying in a vast triangular formation, millions of kilometers apart, connected by lasers. This giant observatory will float freely in space, shielded from the terrestrial vibrations that plague ground-based detectors, and will be exquisitely sensitive to the low-frequency gravitational wave spectrum. It is in this low-frequency band that the most tantalizing multiverse signals might be hiding. Imagine trying to hear a faint, constant cello note being played in a crowded, noisy room where everyone is shouting. LIGO hears the shouts, the loud, sudden mergers. LISA will be designed to hear the underlying, sustained music of the cosmos, and it is within that music that a note from another reality might be found. The challenge, of course, is monumental. The background din of gravitational waves from countless merging supermassive black holes throughout cosmic history will create a stochastic hum of its own, a cosmic chorus that could easily drown out a solitary alien note. Disentangling one specific signal from this background will require not just sensitivity, but brilliant data analysis techniques. Scientists will need to search for a signal that is too perfect, too monochromatic, and perhaps too constant to be explained by any known astrophysical source within our universe. It would be a signal that doesn't fit any of our models, a clear outlier that points to a physics beyond our own. The excitement lies in the possibility that these waves could carry encoded information about the nature of the other universe, perhaps about the strength of gravity there, or the properties of its fundamental fields, offering us a first glimpse into the laws that govern a reality entirely separate from our own. But what if the evidence of a cosmic collision isn't just a subtle pattern in the light or a faint ripple in spacetime, but something far more fundamental? A change in the very rules of the game. We take for granted that the laws of physics are the same everywhere. The speed of light in a vacuum is always exactly 299,792,458 meters per second. The strength of gravity, the charge of an electron, the fine structure constant that governs how atoms interact with light, these are the unchanging pillars upon which all of modern science is built. They are considered constants for a reason. Yet, the breathtaking idea emerging from multiverse theories is that these constants might not be universal laws at all, but rather local bylaws specific to our particular cosmic bubble. And if another universe were to collide with ours, the resulting shockwave could potentially create a region where these fundamental rules are slightly, but detectably, different. Imagine a scenario where the collision imparts enough energy to temporarily destabilize the quantum fields that define our reality. In such a turbulent zone, the values that we hold constant could fluctuate. Perhaps in a specific direction of the sky, the fine structure constant denoted by the symbol alpha might be a fraction of a percent larger or smaller. This might not sound like much, but the implications are seismic. A change in alpha would directly affect how atoms absorb and emit light. The spectral lines of distant elements, which act like unique barcodes for astronomers, would appear subtly shifted in a very specific way that cannot be explained by the standard Doppler effect of an expanding universe. It would be as if the very language of light itself had a different accent in that part of the cosmos. This isn't just wild speculation. Scientists have actively been searching for such variations for decades. In the late 1990s, a team led by astronomer John Webb analyzed the light from incredibly distant quasars, the brilliant cores of active galaxies, as it passed through ancient clouds of gas. By studying the absorption lines from elements like iron and magnesium, they claim to have found evidence that the fine structure constant was slightly smaller billions of years ago and in a certain region of space. This announcement sent shockwaves through the physics community. The claim remains highly controversial, with other teams performing their own analyses and getting conflicting results. The observational data is at the very limit of what our largest telescopes can achieve, and potential systematic errors are a constant concern. But for multiverse theorists, these controversial findings are tantalizing. Could they be the first faint hint that the constants are not locked in place? If a collision with another universe occurred long ago and far away, it could have created a vast, fossilized region where the laws of physics were slightly tweaked, and the light from quasars passing through that region would carry that alien signature to our telescopes today. The search has since expanded. Astronomers now look for not just changes in alpha over time, but also directional dependencies. Does the value of a constant change depending on which way you look in the sky? This would be an even stronger hint of a localized anomaly, a permanent scar from a past collision. Other constants are under scrutiny too. Could the proton-to-electron mass ratio vary? A change here would alter the fundamental properties of molecules. The search involves incredibly precise laboratory experiments on Earth, comparing atomic clocks over years to see if their delicate tick-tock changes, and observations of the most distant astrophysical phenomena we can find. The null result from these searches is just as important, as it places ever tighter constraints on how much our local physical environment can change. But the mere possibility that such a discovery could be made forces us to confront a staggering implication. Our entire edifice of physics, from Newton's apple to the Higgs boson, is built on the assumption that these constants are, well, constant. If that foundation is shown to be shaky, if the rules can change from one place to another, it would mean that physics as we know it is not the fundamental theory of everything, but merely the local zoning code for our particular neighborhood in the multiverse. But what if the impact of a cosmic collision goes far beyond altering physical constants or leaving gravitational ripples? What if it fundamentally warps the very fabric of time itself within the scar tissue it leaves behind? We are so accustomed to time as a steady, relentless river flowing in one direction, but the equations of general relativity tell us this is just a local experience. Space-time is a dynamic entity, and a traumatic event like a collision with another universe could twist it into configurations that defy our everyday intuition. Imagine a region of space where the collision's shockwave didn't just ripple through space, but knotted the relationship between space and time, creating a pocket where the arrow of time bends, loops, or even points in a different direction altogether. Theoretical models that allow for such bizarre possibilities often involve what physicists call closed time-like curves. In simple terms, this is a path through spacetime that loops back on itself, allowing an object to return to its own past. While this sounds like the premise of a science fiction novel, it emerges as a mathematically consistent solution in certain extreme scenarios within Einstein's theory. A universe collision, with its immense concentration of energy and profound distortion of local geometry, could be one of the few events powerful enough to actually create such a structure. In the turbulent aftermath of the impact, the very topology of spacetime might be altered, stitching together points in time in a way that is entirely foreign to the rest of our smoothly expanding cosmos. An observer passing through such a zone might witness events unfolding in reverse or find themselves in a causal loop where the effect precedes the cause, turning the fundamental principle of causality on its head. To make this abstract notion more relatable, consider a simple thought experiment. Picture a calm, flat pond. This represents the regular, uneventful flow of spacetime in our universe. Now imagine two powerful waves, each originating from a different universe, crashing into one another. At the point of their violent intersection, the water doesn't just splash. It might form a swirling vortex, a temporary whirlpool where the water circles back on itself. In this miniature maelstrom, a leaf floating on the surface could be carried in a loop, effectively revisiting the same point in the pond's timeline repeatedly. A cosmic collision could create a spacetime analog of this vortex, a region where the linear progression of time is replaced by a closed, circular path. For anything or anyone within that region, the concepts of before and after could lose all meaning. Of course, physicists don't just dream up these ideas without considering how to test them or what constraints reality might impose. The first line of defense is mathematical consistency. The equations must work without producing logical paradoxes like the infamous grandfather paradox, where a time traveler prevents their own existence. Some theories, like Nobel laureate Roger Penrose's conformal cyclic cosmology, play with the idea of infinite cycles of universes, where the end of one eon's long epoch becomes the Big Bang of the next, though this doesn't necessarily involve localized time loops. When it comes to observational evidence, scientists would look for anomalies that cannot be explained by any other means. For instance, if we observed a distant galaxy where certain cosmic events like supernova explosions appeared to be happening in a statistically impossible sequence, or if the light from a quasar showed signs of interacting with itself from a future state, these could be potential, though highly speculative, hints of disturbed time. The relentless tick of atomic clocks on satellites in our GPS network already have to be corrected for the subtle time dilation effects predicted by general relativity due to their speed and altitude. Finding an unexplained, persistent anomaly in the timing signals from a specific region of space, after accounting for all known factors, would be an electrifying discovery that could point toward a deeper fracture in the temporal landscape. This exploration takes us to the very frontier of theoretical physics, a place where established science bleeds into profound speculation. It forces us to confront the nature of time itself. Is it a fundamental property of the universe, or merely an emergent illusion born from the way we perceive cause and effect? The possibility that a collision with another reality could shatter our local experience of time is a staggering concept, one that challenges not only our understanding of the cosmos but the very nature of reality and our place within it. To truly grasp how universes might collide, we have to venture beyond the captivating imagery and into the world of mathematics, where these incredible ideas are forged into testable hypotheses. This isn't about wild speculation. It's about applying the rigorous language of physics to model the seemingly impossible. Two primary frameworks allow us to do this: the cosmic scale gravity of Einstein's general relativity, and the multi-dimensional landscapes of string theory. General relativity treats spacetime as a dynamic, flexible fabric, and within its equations we can actually model what happens when two distinct regions of spacetime, each potentially with its own geometry and energy, meet. The key tool for this is something known as the Israel junction conditions, named after physicist Werner Israel. Think of it like this: if you have two different materials, say a sheet of rubber and a sheet of silk, and you want to sew them together seamlessly, the stitches at the boundary have to follow specific rules so the join isn't lumpy or torn. The Israel junction conditions are the mathematical rules for stitching two different spacetimes together. They ensure that at the boundary of a collision, the energy and momentum flow smoothly from one universe into the other, preventing any physical impossibilities. This allows theorists to build stable, mathematically consistent models of colliding bubble universes and calculate what kind of ripples or imprints such an event would leave behind. String theory offers an even more radical canvas for these collisions through the concept of the brane world. In this view, our entire universe might not be a bubble of spacetime floating in a void, but a three-dimensional membrane, a brane for short, drifting within a higher dimensional space called the bulk. Other universes could be other branes parallel to our own in these extra dimensions. A collision, in this scenario, isn't a merger of bubbles but more like two slices of bread in a vast, higher dimensional loaf smacking into each other. This braneworld paradigm was hugely influenced by the work of theorists like Leonard Susskind, a founding father of string theory. The mathematics here involves describing how these membranes vibrate and move through the bulk and what happens when their paths cross. The energy released in such a brane collision could be astronomical, and some models even suggest it could be the very source of the Big Bang that created our universe, turning a collision into a genesis event. Another crucial mathematical concept is quantum tunneling between vacua. The word vacuum in physics doesn't mean pure emptiness. It means the state of lowest possible energy for a field. But our vacuum might not be the only one. The Higgs field, for instance, could potentially have different stable states with different energy levels. Our universe exists in one specific low-energy vacuum state. Through the weird probabilistic rules of quantum mechanics, it's theoretically possible for a tiny region of space to spontaneously tunnel through an energy barrier into a different vacuum state, nucleating a new universe bubble with entirely different physical laws. This process is described by equations that calculate the probability of such an event, balancing the energy of the new vacuum against the tension of its boundary. The prolific cosmologist Max Tegmark has explored the mind-bending implications of this, categorizing different types of parallel universes that could arise from these fundamental principles. His work helps formalize the discussion, moving it from philosophical wonder into a structured scientific framework that can be analyzed and debated. The common thread weaving through all these mathematical approaches is the use of sophisticated geometry. Whether it's the curvature of spacetime in general relativity or the complex shapes of Calabi-Yau manifolds that define extra dimensions in string theory, the language of these collisions is written in geometry. The equations don't describe things bumping together like billiard balls. They describe how geometries interact, merge, and create new structures. They tell a story of how a spherical boundary might deform, how energy propagates as a shockwave through dimensions we cannot see, and how the fabric of cause and effect might be warped at the point of impact. This mathematical rigor is what separates a scientific hypothesis from a science fiction plot. It forces specificity and allows for predictions. A theorist can run the equations and say, if a collision occurred under these specific conditions, it should produce a circular temperature anomaly in the CMB of a specific size and contrast. This gives observers a precise blueprint to go looking for in the data. The mathematics provides the target, transforming an epic cosmic fantasy into a genuine, if incredibly difficult, search for evidence. Faced with the immense challenge of observing the unobservable, cosmologists have turned to the digital realm, using the raw power of supercomputers to build virtual multiverses where they can stage cosmic collisions on demand. This isn't about creating flashy visual effects. It's a rigorous scientific process of translating complex mathematical theories into dynamic, testable models. The goal is to answer a critical question. If two universe bubbles were to collide, what exactly would it look like from our perspective inside one of them? The simulations begin by defining the fundamental parameters of the colliding universes. Researchers input specific values for properties like the vacuum energy, the inherent energy density of empty space that drives accelerated expansion. They might simulate a collision between a universe like our own with a relatively modest vacuum energy and one with a vastly different value, perhaps much higher or even negative. They also define the dimensionality of space-time, the shape of the potential energy landscape that governs the transition between vacuum states, and the initial conditions of the collision, such as the angle and relative velocity of impact. These parameters are fed into equations derived from general relativity and quantum field theory, which are then solved numerically over billions of iterative time steps. This requires staggering computational resources. Projects like CosmoGrid, a massive international collaboration, leverage distributed supercomputing power to handle the astronomical calculations. The Perimeter Institute for Theoretical Physics in Canada is another hub for this work, where researchers run sophisticated simulations to explore the intricate dynamics of colliding spacetime geometries. The output is not a Hollywood movie, but vast datasets representing the state of the simulated universe at each moment in time. To make sense of this data, scientists use advanced visualization techniques, translating numbers into visual maps of temperature, energy density, and curvature. They can watch as the shockwave from the collision propagates through their digital cosmos, and most importantly, they can calculate what the signature of that event would look like imprinted on the simulated cosmic microwave background. The true power of these simulations lies in their predictive capability. By running thousands of collisions with slightly different parameters, researchers can build a comprehensive library of potential signals. They might find that a head-on collision between two universes with high vacuum energy produces a distinct, sharp-edged cold spot surrounded by a heated ring. A more glancing blow might create a series of concentric ripples or a specific pattern of polarization in the CMB light. This library becomes a crucial field guide for observers. When astronomers analyze data from the Planck satellite, they aren't just looking for something weird. They can run sophisticated statistical comparisons between the real sky and their library of simulated collisions, searching for a match. This transforms the search from a fishing expedition into a targeted hunt for specific, predicted patterns. It allows them to say, if a collision of type X occurred, we should see a signal that looks like Y, giving the entire endeavor a concrete, falsifiable framework that is the hallmark of robust science. Furthermore, these simulations allow scientists to explore the secondary effects of a collision that might be visible in other ways. Could the gravitational wave background contain a specific, persistent frequency triggered by such an event? Might the collision distort the large-scale structure of the universe, creating a subtle alignment of galaxies or an unusual void? By creating these virtual laboratories, cosmologists can explore these multifaceted consequences, generating a whole suite of observational tests that extend far beyond a single anomaly in the microwave background. This computational approach beautifully illustrates the interdisciplinary nature of 21st century cosmology, where theoretical physicists, computer scientists, and data analysts collaborate to push the boundaries of what we can know about the deepest mysteries of existence. While the cosmic microwave background remains a primary hunting ground, scientists are not putting all their eggs in one cosmological basket. The search for echoes from other realities has expanded into a multifaceted endeavor, leveraging everything from the large-scale structure of the universe to the most elusive particles known to physics. One particularly promising avenue is the detailed mapping of the universe's three-dimensional structure. Projects like the Sloan Digital Sky Survey have charted the positions of millions of galaxies, revealing a vast cosmic web of filaments, clusters, and immense voids. A collision with another universe in the distant past could have sent a powerful shockwave rippling through this web, potentially leaving a detectable imprint. Imagine throwing a stone into a spider's web. The intricate patterns of the silk are disturbed in a specific, radiating pattern. A cosmic collision could have done the same to the distribution of matter, creating a subtle but statistically identifiable alignment of galaxies or a series of concentric shells within the large-scale structure that defy standard models of gravitational clustering. Another powerful tool in this search is the phenomenon of gravitational lensing, where the gravity of massive objects bends and distorts the light from more distant galaxies behind them. By studying these distorted images, astronomers can map the distribution of both visible and dark matter. A collision-induced anomaly in spacetime, a region of unusual density or curvature, would act like a hidden lens, creating a specific and unexpected pattern of distortions in the light from background galaxies. Surveys like the Dark Energy Survey and the upcoming Vera-C Rubin Observatory's Legacy Survey of Space and Time are collecting gravitational lensing data on an unprecedented scale. Within this deluge of information, automated algorithms are now searching for strange, isolated lensing effects that don't correspond to any known cluster or galaxy, which could be the signature of a massive, invisible scar, a fossilized remnant of an impact from another reality. Perhaps the most exotic frontier in this search involves not light, but ghostly particles called neutrinos. These nearly massless particles barely interact with matter, allowing them to travel across the cosmos almost completely unimpeded. A colossal event like a universe collision would be a neutrino factory of unimaginable scale, generating a tremendous burst of these particles. While the initial burst would have occurred billions of years ago, a persistent, isotropic background of neutrinos from such events might still permeate the universe. Detecting this background and identifying its specific energy signature is a monumental challenge, but next-generation neutrino observatories like the planned IceCube Gen 2 in Antarctica or the Pacific Ocean Neutrino Experiment are being designed with the sensitivity to probe these deepest of cosmic backgrounds. Finding a diffuse neutrino signal that cannot be explained by known sources like supernova or active galactic nuclei would be another tantalizing piece of the puzzle. The sheer volume of data from these diverse searches is so immense that traditional analysis methods are often insufficient. This is where modern innovation truly shines, with scientists increasingly turning to artificial intelligence and machine learning. These algorithms can be trained on simulated data that includes universe collisions, learning the complex, subtle fingerprints these events would leave across different datasets. They can then sift through the real observational data with a superhuman ability to find patterns and correlations that would be invisible to the human eye. A machine learning system might, for instance, cross-reference a faint, unusual pattern in galaxy distribution with a specific set of gravitational lensing anomalies and a slight excess of neutrinos in a particular region of the sky, piecing together a case for a collision that no human researcher could have connected. This approach represents a paradigm shift, moving from testing a single hypothesis to letting the data itself suggest new and unexpected possibilities. It is crucial to remember that in science, not finding something is just as important as finding it. Each of these searches, even when they come up empty, helps to narrow down the vast landscape of theoretical possibilities. A null result from galaxy surveys places tighter constraints on how violent a nearby collision could have been without leaving a visible trace in the cosmic web. The absence of a specific lensing anomaly rules out certain types of collision-induced spacetime defects. This process of elimination is how science slowly and methodically corners the truth, winnowing down the range of viable theories. The fact that no definitive multi-messenger evidence for a universe collision has yet been found tells us that if these events happen, they are either exceedingly rare, incredibly subtle, or so alien that their signatures are beyond our current capacity to imagine or detect. Yet, this lack of evidence has done nothing to dampen the curiosity driving this search. It has only refined the questions and inspired more creative ways to listen for the whispers of other realities. This journey into the multiverse inevitably pulls us from the clean equations of physics into the profound and often unsettling waters of philosophy, confronting the possibility that we are not alone in a singular cosmos, but merely one conscious fragment in an infinite tapestry of realities, forces a radical re-evaluation of our place in existence. It dismantles the notion of human uniqueness on a cosmic scale. For centuries, we have operated under the assumption that our universe is all there is, a special stage upon which the human story uniquely unfolds. But if the multiverse is real, then our stage is one of countless millions, and the probability that our specific combination of physical laws, historical events, and conscious life is repeated elsewhere approaches near certainty. The philosopher Nick Bostrom has explored this deeply, suggesting that in such a vast ensemble, every possible version of you, me, and every decision ever made is realized in some other branch of reality. This doesn't diminish our individual experiences, but it does challenge the cherished idea that our narrative is a singular, special occurrence in the grand scheme of things. This leads directly to the haunting question of life in these other realms. Would universes with different physical constants even allow for the complex chemistry necessary for biology as we understand it? In a cosmos where the strong nuclear force is slightly weaker, atoms might never coalesce. In one where the cosmological constant is vastly larger, the universe might rip itself apart before the first star even forms. Yet, within the infinite variety of the multiverse, there must be realms where conditions, while alien to us, are perfectly suited for forms of life and consciousness we cannot possibly imagine, entities built not on carbon and water, but on entirely different substrates, perceiving dimensions we cannot access and experiencing time in a non-linear flow. The physicist David Deutsch argues that this vastness actually elevates the importance of knowledge. If all possible environments exist, then the specific explanations we develop in our universe, the laws of physics, the principles of computation, become universal truths, applicable across the multiverse and granting our quest for understanding a truly cosmic significance. What then of purpose if our choices simply spin off alternate versions of ourselves in branching timelines? Does our decision-making lose its weight? If every tragedy is avoided somewhere and every failure is a triumph in another reality, does it render our struggles and triumphs here meaningless? Many philosophers argue the opposite. This perspective doesn't negate the value of our lived experience. It liberates it from a predetermined cosmic purpose. Our purpose isn't written into the universe. It is something we create and define for ourselves within this particular narrative strand. The value of a good life isn't diminished because other good lives are being lived elsewhere. In fact, it might enhance the preciousness of our specific, shared journey here and now, making our local acts of kindness, creativity, and curiosity all the more vital because they represent a unique expression of consciousness in this particular corner of the multiverse. This is the ultimate philosophical implication, a shift from seeking a purpose handed down by the cosmos to embracing the responsibility and freedom of crafting our own meaning within it. This relentless pursuit of cosmic echoes is a dance on the razor's edge between discovery and delusion, where the most seductive signal can often be a mirage. The history of science is littered with the ghosts of breakthroughs that weren't, tantalizing anomalies that captured the world's imagination before fading away under the harsh light of further scrutiny. Take the pioneer anomaly, for instance. For decades, scientists were utterly baffled by the unexpected, tiny but persistent deceleration of the Pioneer 10 and 11 spacecraft as they journeyed into the outer solar system. This minuscule deviation from the predicted path sparked a firestorm of speculation, with some suggesting it was our first hint of entirely new physics, perhaps even a flaw in our understanding of gravity itself. Years of meticulous detective work eventually revealed a far more mundane culprit: the faint, uneven push of heat radiating from the spacecraft's own radioactive power generators. It wasn't a revolution in physics, it was a subtle thermal effect that had been overlooked. An even more dramatic example unfolded in 2011 when the Opera experiment made an earth-shattering announcement. Their measurements appeared to show neutrinos traveling from CERN in Switzerland to a detector in Italy, arriving a fraction of a second faster than the speed of light. This wasn't just an anomaly, it was a direct violation of Einstein's theory of special relativity, the very foundation of modern physics. The scientific world was sent into a frenzy. But that excitement was short-lived. The culprit once found was almost embarrassingly simple: a faulty fiber optic cable connection and a mis-synchronized clock within the experiment's own timing system. The neutrinos had been obeying the cosmic speed limit all along. These cautionary tales are not failures of science, they are science working as it should, with built-in self-correction and a healthy, necessary dose of skepticism. To guard against these false positives, cosmologists employ a rigorous statistical arsenal. The gold standard is the 5 sigma significance level. In simple terms, this means that the probability of a detected signal being a random fluke in the data is about 1 in 3.5 million. It's an incredibly high bar set specifically to prevent us from being fooled by chance. But even this isn't foolproof, thanks to a sneaky problem known as the look elsewhere effect. If you search an entire sky map of the cosmic microwave background for any unusual feature, the odds of finding something that looks strange by pure accident are actually quite high. It's like searching a vast beach for a perfectly round stone. You will eventually find one, but that doesn't mean it was placed there by design. Scientists must therefore adjust their statistical significance to account for the sheer size of their search area, making the standard even more stringent. Beyond statistics, the most powerful tool is independent verification. A potential discovery isn't confirmed until a completely different team, using a different instrument or a different analysis method, finds the exact same signal. This process of replication is the bedrock of the scientific method, a firewall against instrumental errors, hidden biases, and collective wishful thinking. It's why the initial tantalizing hints of bubble collisions in the Planck data, while exciting, remain just that, hints. They have not been independently confirmed by other experiments. and alternative analyses of the same data often offer more conventional explanations. This slow, deliberate, and often frustrating process is the price of doing business at the frontier of knowledge. It forces researchers to be their own most ruthless critics, to spend years chasing down every possible mundane explanation before even whispering the word breakthrough. This culture of caution is what separates solid science from sensationalism, ensuring that if we ever do hear a true echo from another reality, the evidence will be so overwhelming and so thoroughly vetted that it will undoubtedly change our world. The hunt for these cosmic whispers is entering a thrilling new era, driven by a suite of next-generation instruments so powerful they border on the magical. These aren't just incremental upgrades, they represent a fundamental leap in our ability to perceive the universe's most subtle secrets, offering our first real chance to move from theoretical speculation to tangible evidence. Leading this charge is the James Webb Space Telescope, already revolutionizing our view of the cosmos. While its primary mission focuses on the first galaxies and the atmospheres of exoplanets, its unparalleled infrared sensitivity is a secret weapon in the multiverse hunt. Webb can peer deep into the cosmic microwave background's polarization with a clarity never before possible, searching for those telltale, swirling B-mode patterns that could be the signature of a primordial gravitational wave, a potential echo from a collision at the dawn of time. Its ability to see through obscuring dust also allows for meticulous studies of the large-scale structure of the universe, searching for any bizarre alignments or vast, unnatural-looking voids that might be the fossilized scars of an ancient impact. But the true dedicated hunter of the CMB's faintest murmurs is the upcoming project known as CMB-S4, the Cosmic Microwave Background Stage 4. This isn't a single telescope, but a coordinated army of them. Imagine a vast network of ultra-sensitive detectors deployed at the South Pole and in the high Chilean Andes, scanning the sky continuously for years on end. The goal is to map the temperature and polarization of the CMB with a resolution and sensitivity that will make the Planck satellite's incredible maps look like a rough sketch. CMB-S4 will effectively listen to the universe's background static with such precision that it could detect a temperature variation 100 times fainter than what we can see today. This is the experiment specifically designed to either confirm the exotic patterns predicted by collision simulations or to finally rule them out with definitive authority. It will be able to distinguish between a true primordial signal and the foreground pollution from our own galaxy with surgical precision, cutting through the cosmic noise to reveal the pristine whisper of the Big Bang itself. On the gravitational wave front, the future is equally breathtaking. While LIGO listens to the high-frequency chirps of stellar mass collisions, the Laser Interferometer Space Antenna, or LISA, will open an entirely new window onto the cosmos by hearing the low-frequency hum. Scheduled for launch in the next decade, LISA will consist of 3 spacecraft flying in a perfect triangular formation, separated by 2.5 million kilometers, connected by lasers. This giant floating interferometer will be impervious to the seismic rumble that limits ground-based detectors, allowing it to tune into the deepest gravitational bass notes in the universe. In this low-frequency band, LISA could detect the persistent monochromatic hum of a cosmic string, a hypothetical defect in space-time, or the long-duration ringing from a universe collision that occurred billions of years ago. It will be listening for a melody that doesn't belong to any known astrophysical instrument, a pure tone that could only be produced by something as cataclysmic as the meeting of two realities. Pushing this even further is the proposed Einstein telescope, a third-generation gravitational wave observatory planned for deep underground in Europe. Designed to be 10 times more sensitive than current detectors, the Einstein telescope will effectively bring the entire history of black hole mergers in the universe into audible range. But its exquisite sensitivity also makes it a perfect instrument for searching for the stochastic gravitational wave background, the faint, collective hum from all the unresolved sources throughout cosmic history. Buried within that hum could be a unique contribution from a population of universe collisions, a specific frequency signature that would stand out like a lone cello in a symphony orchestra. The combined data from LISA and the Einstein telescope will give us a gravitational wave spectrum spanning an incredible range of frequencies, offering multiple, independent ways to cross-check any potential discovery. Beyond these flagship projects, innovation is happening on every front. Spectroscopic surveys like the Dark Energy Spectroscopic Instrument are creating unprecedentedly detailed three-dimensional maps of millions of galaxies, providing a new canvas on which to search for the distorted large-scale structure left by a collision shockwave. Next-generation neutrino observatories are being designed to detect the faintest backgrounds of these ghostly particles, potentially sensing a diffuse flux from events too ancient and powerful to comprehend. And underpinning all of this is the power of artificial intelligence, which will be essential for sifting through the petabytes of data these new instruments will produce, finding the subtle, complex correlations that human eyes would never see. The promise of these tools is not that they will make the search easy, but that they will finally make it fair. They are giving us a fighting chance to hear the universe's quietest secrets, offering the very real possibility that within the next decade or two, we might finally know if the echoes we've been searching for are real, or if we are truly alone in the silence. But if the fabric of reality is a multiverse, then the spooky connections of quantum mechanics might not be limited to our own cosmic neighborhood. This leads us to one of the most speculative and mind-bending frontiers of all, the possibility that quantum entanglement could somehow operate across the boundaries separating different universes. In our own reality, entanglement is bizarre enough, a phenomenon Einstein famously called spooky action at a distance, where two particles can become linked in such a way that measuring the state of one instantly determines the state of the other, no matter how far apart they are. Now, stretch this concept to its ultimate extreme. If the many worlds interpretation of quantum mechanics is correct, and every quantum decision spawns a new branch of the universe, could particles in these now separate branches remain entangled with each other? It's a staggering thought, a subatomic connection that doesn't just cross space but bridges entirely different realities. This isn't just philosophical wonderment, it's a concept some theorists are trying to formalize. They explore models where the wave function, which describes the probabilistic state of a quantum system, doesn't just collapse into a single outcome in our universe. Instead, it continues to embrace all possibilities, with each outcome being realized in its own branching world. In this view, the moment of measurement isn't a collapse but a decoherence, a splitting of the cosmic tapestry into parallel threads. And if those threads were once part of the same whole, perhaps a subtle quantum connection persists, like an invisible thread tying the different versions of a particle together across the vast landscape of the multiverse. You could imagine a scenario where performing a specific experiment in our universe somehow influences the probability of an outcome in another, not by sending a signal, but through this underlying, fundamental link that predates the branching of reality itself. The implications become even wilder when we consider regions where universes have collided. A collision zone would be a place of immense energy and unimaginable distortion of local physics. In such a turbulent environment, the normal rules of quantum mechanics might be temporarily suspended or dramatically altered. How would wave function collapse if it even occurs? work in a place where the fabric of space-time itself is knotted and frayed. It's conceivable that a collision could create a kind of quantum bridge, a temporary tunnel where information or influence could, in theory, leak between realities. These concepts, often discussed in the context of wormholes or Einstein-Rosen bridges, suggest that the intense gravity and energy of a collision might forge a transient connection that allows the quantum states of the two universes to briefly interact or become entangled. To make this abstract idea a bit more tangible, think of the multiverse not as a collection of separate bubbles, but as a vast, multidimensional tapestry. Each universe is a unique thread woven into this grand design. Now, imagine that at the quantum level, some of these threads are not simply lying side by side. They are subtly intertwined, stitched together in a complex pattern that we are only beginning to imagine. A particle in our universe and its counterpart in another might be like 2 points on this single, entangled thread, forever linked no matter how far the tapestry expands. This isn't a perfect analogy, but it helps visualize a connection that transcends the conventional dimensions of space and time. It is crucial to ground this exciting speculation in a firm dose of scientific reality. These ideas, while intellectually thrilling and mathematically explorable, remain entirely in the realm of theory. There is not a shred of empirical evidence for quantum entanglement across universes. It is a hypothesis that currently sits at the very edge of testability, if it can be tested at all. The many worlds interpretation itself, while a popular and elegant solution to the puzzles of quantum mechanics, is just that, an interpretation. It makes the same predictions as other interpretations, like the Copenhagen interpretation, so distinguishing between them experimentally has proven to be incredibly difficult. Proposing a connection between these worlds adds another layer of complexity that currently lies beyond our experimental reach. The mathematics involved is formidable, often drawing on advanced concepts in quantum field theory and the geometry of higher dimensions, and it remains a niche area of theoretical physics pursued by a small number of dedicated thinkers. For now, the quantum threads connecting universes are threads of imagination, woven from the mathematics of possibility rather than the fabric of observed reality. They represent a breathtaking direction for thought, a testament to the human capacity to ask ever deeper questions about the nature of existence, even if the answers remain, for the moment, hidden from view. While we push the boundaries of science with telescopes and supercomputers, it's worth pausing to recognize that the human fascination with other worlds is anything but new. Long before the equations of general relativity or the many worlds interpretation, our ancestors were gazing at the stars and telling stories that grappled with these very same ideas. Across countless cultures and millennia, we find a recurring theme, a deep, intuitive sense that our reality is not the only one. These ancient narratives, rich with symbolism and meaning, offer a fascinating parallel to the multiverse theories we're exploring today, suggesting a timeless human drive to understand our place within a cosmos that might be far vaster than it appears. Consider the vast and intricate cosmology of Hinduism, one of the oldest continuous religious traditions in the world. It doesn't speak of a single creation event, but of an endless, rhythmic cycle of birth, death, and rebirth for the universe itself. Time is divided into immense units called kalpas, each one lasting over 4 billion years, which is just a single day in the life of the creator god Brahma. Within this framework, our entire universe is but one bubble in an endless foam of creation. The scriptures describe countless other universes, each with its own Brahma, its own laws, and its own destiny, all existing simultaneously. This isn't a vague suggestion. It's a detailed cosmological model that has been contemplated for thousands of years, a profound philosophical answer to the question of what exists beyond the limits of our own perception. The parallels to the modern scientific concept of eternal inflation and a multiverse of bubble universes are, at the very least, striking. This theme of layered realities is echoed in the spiritual traditions of many indigenous cultures across the Americas. Numerous tribes, from the Navajo in the southwestern United States to various First Nations in Canada, hold beliefs in multiple worlds or dimensions that coexist with our own. Often, these are not distant realms but layers of reality that are intimately connected to our world, accessible through vision quests, rituals, or specific sacred sites. In these traditions, the spirit world is not a metaphorical concept but a parallel plane of existence, a reality as tangible to the spiritual senses as our physical world is to our body. These stories served as a way to explain the mysteries of life, death, and the unseen forces that influence the world, creating a holistic world view where everything is interconnected across different layers of being. They represent a different way of knowing, one based on deep observation of nature and spiritual revelation, yet they arrive at a similar conclusion: our world is not alone. We can even look to the ancient Greeks for early philosophical seeds of this idea. The philosopher Democritus, over 2 millennia ago, theorized that the universe was composed of an infinite number of atoms moving through an infinite void. He reasoned that given enough time and space, these atoms would inevitably form every possible combination, not just once, but an infinite number of times. This led him to the logical conclusion that there must be innumerable other worlds, some like our own, some utterly different, scattered throughout the cosmos. While his atomic theory was a physical speculation rather than a mythological story, it shares the same foundational impulse to extrapolate from the local to the cosmic and imagine the possibilities inherent in infinity. So, what are we to make of these parallels? It's a captivating thought that our ancestors, through myth, philosophy, and spiritual insight, might have intuitively grasped a profound truth about the cosmos that science is only now beginning to formalize with mathematics and technology. Perhaps these stories are more than just fanciful tales. Perhaps they represent a deep, almost archetypal human understanding that reality is far more complex and multifaceted than it seems. It suggests a universal human curiosity that transcends time and culture, a shared yearning to peek behind the curtain of the everyday and wonder what else might be out there. However, we must tread very carefully here. While the similarities are evocative, it is crucial to avoid the trap of conflation, of mistaking powerful metaphor for literal scientific evidence. Ancient cosmologies were not intended to be scientific theories in the modern sense. They were primarily spiritual, philosophical, and moral frameworks designed to help people understand their place in the world, explain natural phenomena, and codify cultural values. The Hindu concept of multiple universes exists within a context of karma and spiritual liberation. Indigenous stories of other worlds are deeply tied to specific relationships with the land, ancestors, and the natural world. To strip these rich narratives of their cultural and spiritual context and simply mine them for ideas that resemble modern physics does a great disservice to their original meaning and depth. The most respectful and insightful approach is to see these ancient ideas not as primitive science, but as a different kind of truth-telling. They represent humanity's long-standing attempt to use the tools available, story, symbol, and spiritual experience to grapple with the biggest questions of existence. Science uses mathematics and empirical observation. Our ancestors used myth and revelation. Both are valid paths to understanding, but they speak different languages and serve different primary purposes. The true wonder lies in the convergence of the quest itself, The fact that a 21st-century cosmologist running simulations on a supercomputer and a thousands of years old Vedic sage contemplating the cycles of time could arrive at such strangely similar visions of a multifaceted reality is a testament to the boundless creativity and curiosity of the human spirit. It reminds us that our drive to explore the nature of reality is a fundamental part of who we are, a thread that connects us across the centuries, all gazing up at the same stars and dreaming of what other worlds might lie beyond. The moment we confirmed the existence of another universe would instantly become one of the most profound turning points in human history, catapulting us from a species studying a single cosmos to a civilization aware of a grander, multi-reality existence. This staggering revelation would immediately force upon us a monumental ethical dilemma. If they are out there, should we even try to say hello? The science fiction trope of reaching out to the unknown, from contact to arrival, has long explored the potential perils and promises of first contact. But those stories are set within our own universe, governed by the same physical laws. Communicating with a reality operating under a completely different set of rules is a proposition so alien that our standard playbook would be utterly useless, plunging us into an ethical wilderness with no map to guide us. On one side of this debate lies the compelling argument from curiosity and potential benefit, the essence of the scientific and human spirit that has always driven us to explore. Imagine the unimaginable knowledge we could gain from a civilization that has mastered physics we can't even conceive of. A universe where the speed of light isn't a limit, where entropy can be reversed, or where time is a dimension that can be navigated like a river, could offer solutions to our most intractable problems. Limitless clean energy, the end of disease, perhaps even the key to overcoming our own cosmic mortality. This wouldn't be a simple cultural exchange. It would be a leapfrogging of our entire understanding of reality, a shortcut through millennia of scientific struggle. The potential for advancing all of humanity, and perhaps even ensuring our long-term survival, is an almost irresistible lure, a siren call from the edge of existence itself. Yet the counterargument, rooted in a deep and prudent caution, is equally powerful. This perspective asks us to consider the darkest scenarios from science fiction not as entertainment, but as legitimate cautionary tales. The central, terrifying unknown is intent. We would have absolutely no frame of reference for understanding the motivations or morality of an intelligence that evolved in a reality with different fundamental constraints. Their very concept of self, of other, of right and wrong could be so alien that peaceful coexistence might be an impossible concept for them to grasp. What if their universe is resource-starved, and our reality represents a new territory to colonize or consume? A collision between universes suggests that some form of energy or information can cross the boundary, which could be exploited. Our attempt to send a friendly hello might not be perceived as a greeting, but as a dinner bell, inadvertently inviting a force we cannot comprehend and could never hope to defend against. The potential downside isn't just our own destruction. It could be the unraveling of the physical laws of our entire universe, a catastrophe on a scale so absolute it defies description. Beyond the existential risks, we must also confront the sheer practical impossibility of the task. Communication requires a shared medium, a common language of particles and forces. How do you send a message when you don't share the same constants? A signal encoded in electromagnetic waves might be completely unreadable in a universe where photons behave differently or don't exist at all. Our most advanced radio transmission would be as meaningless as static to them. Any attempt to communicate might first require a century of fundamental physics, just to identify a potential carrier wave that could traverse the inter-universal void, a project that would make the Apollo program look like a simple school science fair experiment. The energy requirements alone could be astronomical, diverting vast global resources for an endeavor with an infinitesimally small chance of success, raising the ethical question of whether such an effort would be a responsible use of human capital when so many pressing problems exist right here in our own world. This leads us to the most philosophical layer of the dilemma. What is our responsibility as a species if we are the first in our local multiverse neighborhood to become aware of this greater reality? Does that bestow upon us a duty of care? Perhaps the safest and most ethical course is one of quiet observation, to listen intently for billions of years before ever considering a whisper. We might adopt a kind of prime directive for the multiverse, a self-imposed rule of non-interference born from humility. Our role would not be as conversationalists but as cosmic naturalists, documenting the incredible diversity of existence without disturbing it. This passive approach acknowledges our profound ignorance and the potential fragility of realities beyond our own. It accepts that some mysteries are not meant to be solved, but simply appreciated from an awestruck distance, preserving the integrity and safety of all involved in a cosmic balance we are only just beginning to sense. This profound mystery of our universe's apparent perfection brings us to a concept that sits at the very heart of cosmology and philosophy, the anthropic principle. It's the simple yet deeply unsettling idea that the universe we observe must be compatible with the existence of observers like us. Think of it this way: if any one of dozens of fundamental constants were even slightly different, life as we know it would be utterly impossible. If the force that holds atomic nuclei together were just a few % stronger or weaker, stars might never form or would burn out in a cosmic instant. If the amount of dark energy were greater by a minuscule fraction, the universe would have expanded so rapidly that not a single galaxy could have ever coalesced. The list of these cosmic coincidences is long and incredibly precise, pointing to a universe that seems almost engineered for our existence. This is the puzzle of fine-tuning, a riddle that demands an explanation. The multiverse theory offers a powerful, if somewhat dizzying, solution to this riddle through the lens of the anthropic principle. If our universe is just one of a possibly infinite number of universes, each with its own random set of physical laws and constants, then it's no wonder we find ourselves in one of the rare habitable ones. We couldn't possibly be in a universe that doesn't allow for our existence. In this view, there is no grand designer or deeper reason for the fine-tuning. It's simply a matter of statistical inevitability given a large enough sample size. It's like winning the cosmic lottery, but if the lottery had an infinite number of tickets, someone had to win, and we are that lucky someone. This application of the anthropic principle is often called the weak form, as it doesn't require any special purpose, just a vast landscape of possibilities. Now consider how the concept of cosmic collisions weaves into this tapestry. If universes can collide, these violent events might not just leave behind scars in the cosmic microwave background. They could potentially create localized regions within a universe where the fine-tuning is slightly different. Imagine a shockwave from a collision rippling through our cosmos in its earliest moments, slightly altering the values of fundamental constants in a specific, vast region of space. This wouldn't create a new universe but a kind of bubble within a bubble, a domain with its own unique physical bylaws. In such a scenario, the anthropic principle would operate on a local scale. We would exist in the hospitable part of our universe simply because that's the only place we could have arisen, blissfully unaware of neighboring regions where the laws of physics are hostile to any form of complex structure, let alone life. This idea sparks a fierce and ongoing debate among physicists and philosophers. Proponents of the multiverse argue that it provides the most natural, non-mystical explanation for fine-tuning. It takes a seemingly miraculous set of coincidences and reframes it as a selection effect. We are here because this is one of the places that allows us to be here. Prominent thinkers like Max Tegmark and the late Stephen Hawking found this reasoning compelling. However, critics counter that the multiverse solution is a philosophical cop-out. They argue that it doesn't truly explain fine-tuning, it merely shifts the problem up one level. Instead of asking, why is our universe so finely tuned? We are now left asking, why is there a multiverse with the right rules to produce a finely tuned universe? Physicists like Paul Davies and David Gross have pointed out that invoking an infinite number of unobservable universes can make any observation seem inevitable, potentially halting the search for a deeper, more elegant physical theory that could explain our universe's parameters from first principles. This debate connects to the deepest issues of all. Why is there something rather than nothing, and why is that something structured in this specific, life-allowing way? The multiverse and the anthropic principle offer one type of answer, one that embraces chance and vastness. Yet, the human desire for a more satisfying explanation persists, leading scientists to explore other possibilities that don't require an infinity of unseen worlds. Some theorists pursue the dream of a final theory, a single, elegant equation from which all the constants of nature necessarily flow, making their values not a random accident but a mathematical certainty. Others explore more radical ideas, like the notion that the universe is in some sense conscious or that it fine-tuned itself through a feedback loop across time. Each path represents a different answer to the ancient question of our place in the cosmos, and the search for which one is true remains one of the most thrilling journeys in all of human thought. Despite the captivating allure of a cosmos teeming with parallel realities, the multiverse hypothesis faces a formidable wall of criticism from some of the most respected minds in physics and philosophy. These objections aren't mere nitpicking, they strike at the very heart of what constitutes a scientific theory, challenging whether the multiverse idea is a groundbreaking insight or a philosophical dead end. Leading this charge is Paul Steinhardt, a Princeton physicist who was actually one of the original architects of inflationary theory. Steinhardt has since become one of its most vocal critics, particularly of its eternal, multiverse-generating versions. His core argument is devastatingly simple. If a theory predicts everything, then it ultimately predicts nothing. For an idea to be truly scientific, it must be falsifiable. It must make specific, testable predictions that could, in principle, be proven wrong. If we can always explain any observation, no matter how bizarre, by saying, well, that just happens in our particular pocket of the multiverse, then the theory has effectively insulated itself from any possible disproof. It becomes a textbook example of what philosophers call a non-faultable idea, one that is structured to always be right, which in science is the same as being meaningless. This concern is echoed by other towering figures like David Gross, a Nobel laureate in physics. Gross worries that embracing the multiverse could represent a dangerous retreat from the historic goal of fundamental physics, to find a unique, elegant, and complete theory of everything that explains why our universe must be the way it is. If we instead accept that all possible universes exist, we are essentially giving up on that quest for a deep explanation, replacing it with a cosmic shrug. Why is the cosmological constant so small? Why do the fundamental forces have the strengths they do? The multiverse answer is, because in an infinite ensemble, some universe had to have these values. For critics, this feels like a cop-out, an appeal to chance that avoids the harder, more rewarding work of finding an underlying physical principle that dictates these values necessarily. It swaps the dream of a beautiful, unique equation for a messy, profligate, and ultimately untestable statistical landscape. This leads directly to the problem of infinite regression. The multiverse is often presented as a solution to the fine-tuning problem, but critics argue it merely kicks the can down the road. Instead of explaining why our universe is fine-tuned, we now must explain why the multiverse generator, the specific laws of inflationary physics or string theory that spawn all these bubbles, is itself fine-tuned to produce even one habitable universe. The question, why is our universe so bio-friendly, simply becomes, why is the multiverse generator so bio-friendly? We haven't solved the fundamental mystery, we've just added an extra layer of complexity to it. We are required to believe in a pre-existing, finely tuned meta-law that governs the creation of all universes, which leaves us right back where we started, pondering the same question of origins but on an even more impenetrable scale. Philosophically, the objections are just as sharp. The multiverse concept turns the nature of evidence on its head. In normal science, we use evidence to build and validate a theory. With the multiverse, the reasoning often feels reversed. The theory is used to explain away the evidence. The astounding fine-tuning of our universe isn't taken as evidence for a deeper law or even a designer, but as an inevitable selection effect within an unobservable ensemble. This reliance on anthropic reasoning, we see it because we are here to see it, is viewed by many as a weakening of the scientific method. It risks creating a theory of anything, where no observation can ever truly challenge the core idea because any possible outcome can be accommodated somewhere in the vast multiverse. This doesn't mean the multiverse is wrong, but it does place it in a precarious position, hovering on the boundary between a physical theory and a metaphysical belief system. For a great many thinkers, that is a boundary that science must be careful not to cross, lest it lose its powerful, empirical grip on reality. This journey into the multiverse inevitably brings us to a crucial crossroads, a boundary line as fascinating as it is fuzzy, the line between rigorous science and captivating speculation. Multiverse theories, for all their mathematical elegance and conceptual appeal, currently reside in this precarious borderland. They are not yet firmly in the camp of established empirical science, but they are also far more than mere science fiction. They are serious hypotheses that push the very definition of what science can investigate. To understand this delicate position, we need to consider the bedrock principle that has guided scientific inquiry for over a century: falsifiability. Pioneered by philosophers like Karl Popper, this idea states that for a theory to be truly scientific, it must make specific predictions that could, at least in principle, be proven wrong by observation or experiment. A scientific theory sticks its neck out, inviting the world to try and chop it down. It's this vulnerability to being disproven that separates a scientific claim from an untestable belief. When we hold the multiverse hypothesis up to this light, the challenge becomes immediately apparent. How do you test for the existence of something that, by its very definition, may be permanently beyond our observational horizon? If other universes are causally disconnected from our own, with no possible exchange of information, then any claim about their existence might seem inherently unfalsifiable. Critics argue that this moves the multiverse from the realm of science into the realm of metaphysics, a fascinating philosophical idea, but one that cannot be validated by the scientific method. If we can always explain any observation in our universe by simply saying, well, that's just how things are in our particular bubble, then the theory risks becoming a conversation ender rather than a catalyst for discovery. It could be seen as an easy way to explain away the deep mysteries of fine-tuning and cosmic origins without providing a concrete, testable mechanism. Yet, the history of science is filled with brilliant ideas that started on the speculative fringe before gradually moving into the mainstream as technology and understanding caught up. One of the most powerful examples is the theory of continental drift. When Alfred Wegener first proposed in the early 20th century that the continents were slowly moving across the globe, his idea was met with widespread skepticism and even ridicule from the geological establishment. The mechanisms were unclear, the evidence seemed circumstantial, the neat fit of coastlines, similar fossils on separate continents, and the concept was deemed by many to be unscientific speculation. It wasn't until decades later, with the discovery of plate tectonics and seafloor spreading, that Wegener's radical vision was not only validated but became the central organizing principle of all Earth science. The boundary of what was considered scientific had shifted dramatically, transforming a once dismissed speculation into uncontested fact. The same story unfolded with the concept of atoms. The ancient Greek philosopher Democritus speculated that all matter was composed of tiny, indivisible particles he called atoms. For over 2 millennia, this remained a purely philosophical idea with no empirical support. It wasn't until the 19th and 20th centuries that scientists like Einstein, who studied Brownian motion, and others, through painstaking experimentation, provided overwhelming evidence for atomic theory. What was once abstract speculation became the foundation of modern chemistry and physics. These historical precedents teach us a vital lesson in humility. The line between speculation and science is not fixed. It is a frontier that expands with our ingenuity. An idea that seems untestable today might become testable tomorrow with a new telescope, a more powerful particle accelerator, or a completely new way of thinking about the problem. This is the hopeful perspective that multiverse proponents hold onto. They argue that while direct observation of another universe may be impossible, we can still look for indirect secondary effects within our own cosmos, the very cosmic bruises and gravitational echoes we've been discussing. The search for specific, predicted patterns in the cosmic microwave background is a form of this indirect testing. If a theory predicts that collisions should produce a particular type of circular asymmetry with a specific statistical signature, and we go looking for it and definitively do not find it, that particular version of the multiverse theory could be falsified. Similarly, if we were to ever discover a region of space with fundamentally altered physical constants that defied all other explanations, it would dramatically boost the credibility of the hypothesis. The key is that the theory must make specific, risky predictions about what we should see in our universe, predictions that could be proven wrong. This ongoing tension is not a weakness of science, it is its greatest strength. The scientific process is a self-correcting engine driven by a healthy balance of bold speculation and ruthless skepticism. The dreamers push the boundaries of what we think is possible, while the skeptics demand solid evidence, ensuring that we don't drift too far into pure fantasy. In the case of the multiverse, this dialogue is alive and well. Theorists continue to refine their models, making them more precise and predictive, while observers design ever more sensitive experiments to put those predictions to the test. This process requires immense intellectual honesty from everyone involved. It demands that scientists clearly communicate the speculative nature of these ideas to the public, avoiding sensationalism, while also passionately arguing for the resources to explore them further. For us as observers, it invites a certain open-minded patience, a willingness to entertain spectacular possibilities while understanding that, for now, they remain spectacularly unproven. The most exciting aspect of this entire endeavor is that we simply do not know where the final boundary lies. The universe has consistently proven to be far stranger and more wonderful than we ever imagined, and the ultimate truth about the multiverse may be waiting just beyond the next revolution in our understanding. Pondering the possibility that our entire reality might be just one page in an infinite cosmic library does something profound to the human spirit. It doesn't just expand our understanding of the cosmos, it fundamentally reshapes our internal landscape, our sense of self, and our place within existence. This isn't a cold, abstract scientific exercise, it's a deeply personal journey that can trigger a powerful emotional response. A blend of awe and humility that is both unsettling and strangely liberating. The renowned astronomer Carl Sagan captured this feeling perfectly when he reflected on the famous pale blue dot image, that iconic shot of Earth taken from the edge of our solar system. He noted that our world is just a mote of dust suspended in a sunbeam, a lonely speck in the enveloping cosmic dark. Now, take that profound perspective and multiply it by infinity. If our entire universe, with its hundreds of billions of galaxies, is itself just one mote in a vast multiversal sunbeam, then our individual lives can feel vanishingly small. Yet, Sagan's genius was in flipping that perspective, arguing that this realization should not diminish us, but should fill us with a renewed sense of wonder and a fierce responsibility to cherish our fragile world and the brief moment of consciousness we have upon it. This cosmic humility is the first gift of the multiverse hypothesis. It shatters our egocentric view of creation and replaces it with a breathtaking, if daunting, sense of scale. This shift in perspective inevitably forces us to confront the biggest questions of identity and meaning. If there are infinite versions of reality, does that make our choices here less significant or somehow more so? The philosopher William James wrestled with questions of plurality over a century ago, suggesting that a belief in a single, absolute universe can feel confining, while the idea of a pluriverse feels more free and full of possibility. In a multiverse, every path not taken in our lives is, in a sense, realized somewhere else. The version of you that pursued a different career, lived in a different city, or made a different choice in a pivotal moment, they all exist. This can feel existentially dizzying, as if it dilutes the uniqueness of our personal narrative. But another way to see it is as a celebration of potentiality. It suggests that every possibility is valid, that every dream is realized in some form, and that the constraints of our single timeline do not represent the limits of what could be. It transforms regret into curiosity and reframes our life's path not as a single, fragile thread, but as one vibrant strand in an impossibly rich and complex tapestry of being. Our story is unique not because it is the only one, but because it is the one we are living, experiencing, and shaping with every decision. This exploration also fosters a different kind of connection, not just to the cosmos, but to each other. The astrophysicist and writer Neil deGrasse Tyson often speaks about the cosmic perspective, the feeling of being genetically connected to the universe itself, forged in the hearts of exploding stars. The multiverse concept deepens this connection exponentially. It suggests that every person you meet, every living thing on this planet, is sharing not just a common evolutionary history, but an incredibly rare and specific cosmic address. Out of a possibly infinite array of universes, we all wound up together in this one particular reality that allows for our existence. This shared, staggering improbability can foster a profound sense of kinship and collective wonder. The petty divisions of nationality, culture, and belief begin to seem trivial when viewed against the backdrop of an infinite cosmos. We are all quite literally in this together, inhabitants of the same rare bubble, gazing out at the same mysterious void and trying to make sense of our place within it. This shared cosmic journey can be a powerful antidote to isolation and conflict, reminding us of our common humanity on a pale blue dot that might be one of countless others. Ultimately, the search for echoes from other realities is about more than just mapping the cosmos. It's about understanding the nature of reality itself and our role within it. It pushes the boundaries of human curiosity to their absolute limit and demands a courageous intellectual humility. We are forced to admit that for all our knowledge, we may be like ants trying to comprehend the internet, only glimpsing the tiniest fraction of a truth far grander than we can imagine. This is not a cause for despair, but for endless fascination. It means the universe, or rather, the multiverse, is far more interesting, more complex, and more mysterious than we ever dreamed. It ensures that the fundamental questions of existence will never be fully exhausted, that there will always be another horizon to explore, another whisper to try and hear. This endless curiosity is perhaps our greatest human trait, and it is this drive that propels us to build ever better telescopes, to run immense simulations, and to lie awake at night staring at the stars, wondering what other worlds might be looking back. The journey itself, with all its uncertainties and unanswered questions, becomes a source of inspiration, a constant reminder that we are part of a story that is still being written, across dimensions we are only beginning to conceive. This incredible search for echoes from other realities isn't just reserved for PhDs with access to billion-dollar telescopes. One of the most beautiful aspects of modern cosmology is that it has been flung wide open, inviting anyone with curiosity and an internet connection to join the hunt. This is the world of citizen science, a global movement where millions of everyday people are contributing to real, groundbreaking research. And the quest for evidence of the multiverse is a frontier where your eyes and your intuition can make a genuine difference. Think about the challenge scientists face. They have immense datasets, like the incredibly detailed maps of the cosmic microwave background from the Planck satellite, or the three-dimensional positions of millions of galaxies from surveys like the Sloan Digital Sky Survey. These datasets are so colossal that no single research team, not even a large one, could possibly scrutinize every single pixel or data point for the subtle, strange anomalies that might signal a collision with another universe. Computers are powerful, but they are still not as good as the human brain at recognizing complex, unexpected patterns or spotting something that just looks weird. This is where you come in. Platforms like Zooniverse.org act as a bridge, connecting this deluge of scientific data with the pattern recognition power of volunteers from all over the world. One of the most famous projects is Galaxy Zoo, which began by asking people to help classify the shapes of millions of galaxies. This simple act of categorization is crucial because understanding the large-scale structure of our universe is the first step to identifying anything that might be wrong with it, any vast, unnatural-looking ripple or alignment in the cosmic web that could be the scar of an ancient impact. While Galaxy Zoo itself might not be directly looking for universe collisions, it exemplifies how citizen scientists are trained to become keen observers of cosmic structure. The skills you develop there are exactly what you'd need for more specific multiverse hunting projects. Scientists can create custom tools that allow volunteers to scan CMB maps, searching for those telltale circular bruises or unusual patterns of hot and cold spots that computer algorithms might have missed. Your job would be to flag anything that stands out, bringing it to the attention of researchers for further investigation. Every click, every classification, is a tiny but vital contribution to a massive collaborative filtering process. The process is designed to be accessible and engaging, You typically don't need any prior scientific knowledge. When you log onto a project, you're given a quick, friendly tutorial that teaches you what to look for. You're then shown actual, raw scientific data, an image of a distant galaxy, a heat map of the CMB, a graph of a quasar's light spectrum. You answer simple questions about what you see, and your responses are combined with those of dozens of other volunteers to create a statistically robust result. This collective intelligence is incredibly powerful. It weeds out individual mistakes and highlights the truly intriguing patterns that merit a professional's second look. There's a profound democratization happening here. For centuries, scientific discovery was often confined to a privileged few with access to universities and instruments. Now, a retired teacher in Kansas, a high school student in Kenya, or a night shift worker in Japan can all log on and become a part of humanity's collective effort to understand the deepest nature of reality. You're not just playing a game, you're actively participating in the scientific method, helping to sift through the noise of the cosmos in the hope of finding a signal that would rewrite all of physics. Beyond just classifying existing data, some platforms even allow for more open-ended exploration. The World-Wide Telescope, for instance, is a free software platform that puts a vast amount of astronomical data at your fingertips, allowing you to create your own tours of the universe and explore the skies on your own terms. Who's to say that an amateur astronomer with a keen eye, combing through this public data for their own enjoyment, won't be the first to notice a peculiar void in the galaxy distribution or a strange alignment of cosmic structures that everyone else missed? Some of the most famous discoveries in astronomy, like the original pulsars, were found by sharp-eyed individuals noticing a pattern that didn't fit. The potential for a serendipitous, crowd-sourced discovery is very real. This open access transforms science from a distant, monolithic institution into a living, breathing, collaborative human endeavor. It acknowledges that brilliance and curiosity are not confined to academic institutions, but are distributed throughout the global population, waiting for the right tool and the right dataset to be unleashed. It's a thrilling invitation to stop just watching the journey of discovery and to actually pick up a map and start exploring yourself. So where does this incredible journey take us next? The future of cosmology and the search for evidence of other realities is not a straight path to a single answer, but a sprawling frontier of possibility, branching out in directions we can only begin to imagine. The most exciting breakthroughs are likely to come from a convergence of seemingly unrelated fields, where a discovery in a particle accelerator deep underground could suddenly illuminate a mystery at the edge of the observable universe. Imagine for a moment that the next great clue doesn't come from a telescope at all, but from a machine like the Large Hadron Collider or a future successor, perhaps one that circles the entire planet. As we smash particles together at ever higher energies, we might not just find new particles, we could be probing the very stability of our vacuum. Some theories suggest we might discover that our universe is not in the true lowest energy state, but is instead a metastable false vacuum, a precarious bubble that could, in theory, someday tunnel into a different state with entirely different physics. This wouldn't just be a particle physics discovery, it would be the strongest possible indirect evidence that other vacuum states, and therefore other universes with different laws, are not just possible but inevitable. It would tell us that our cosmic home is not permanent, and that the multiverse is not a distant abstraction, but a potential reality lurking in the very fabric of our existence. Beyond particle smashers, the next century will belong to the silent, patient listeners of the cosmos. We are on the cusp of deploying observatories that will make our current tools seem like primitive curiosities. Think of the James Webb Space Telescope as merely the first step, a pathfinder for a future generation of space-based observatories that will map the cosmic microwave background with such exquisite detail that they will either find the fingerprints of a collision or rule out entire classes of multiverse models for good. On the ground, immense new telescopes like the Vera C. Rubin Observatory will begin a decade-long movie of the sky, capturing changes and anomalies on a scale never before attempted, potentially revealing subtle distortions in the large-scale structure of the universe that whisper of a primordial shockwave. And then there are the gravitational wave astronomers, building ever more sensitive ears to hear the cosmos. The upcoming Laser Interferometer Space Antenna, or LISA, will open a low-frequency gravitational window on the universe, listening for the persistent hum of cosmic strings or the ringing of phase transitions in the early universe that could be the echo of our cosmos settling into its current state amidst a frothing sea of other possibilities. Yet, the ultimate answers may require us to think not just bigger, but fundamentally differently. The holy grail of modern physics remains a theory of quantum gravity, a seamless framework that unites the world of the very small, governed by quantum mechanics, with the world of the very large, described by general relativity. Whether this final theory is string theory, loop quantum gravity, or something entirely new, it must inevitably address the nature of the beginning. A successful theory of quantum gravity will have to tell us what happened at the singularity of the Big Bang, and in doing so, it will be forced to confront the question of what, if anything, came before. Many physicists believe that such a theory will naturally predict a multiverse, not as an add-on or a speculation, but as an intrinsic, unavoidable consequence of its core mathematics. Finding this theory is the grandest challenge in all of science, and it may not come from a single experiment, but from a flash of mathematical insight that redefines our very concepts of space, time, and existence. This long-term quest is a powerful reminder that the journey of discovery holds value far beyond the final destination. Each null result, each experiment that fails to find what we were looking for, is not a failure but a refinement. It pares away the dead ends and sharpens our questions, guiding us closer to the truth. The history of science is a story of failed expectations leading to deeper understanding. We thought the Earth was the center of everything, then the Sun, then our galaxy. With each demotion, our universe became larger and more magnificent. The potential discovery that our universe is just one of many would be the ultimate step in this cosmic humility, but it would also be the ultimate triumph of human curiosity. It would prove that our minds, products of a single tiny planet, are capable of comprehending a reality of literally infinite scope. This pursuit, with all its dead ends and tantalizing hints, expands not just our knowledge of the cosmos, but our understanding of the very process of knowledge itself. It teaches us patience, rigor, and the courage to follow the evidence wherever it leads, even if it leads to a reality far stranger and more wonderful than we ever dreamed. So we've journeyed to the very edge of what we know, exploring the staggering idea that our universe might not be alone, but one of countless cosmic bubbles in a vast multiversal foam. We've seen how these separate realities could, under the right conditions, brush up against one another in collisions of unimaginable scale, potentially leaving faint echoes imprinted on the oldest light in the sky, or as a persistent hum in the fabric of space-time itself. We've delved into the immense challenge of detecting these whispers, a needle in a haystack search that pushes our technology and our ingenuity to their absolute limits, where every potential signal must be scrutinized and every alternative explanation ruthlessly ruled out. And we've pondered the profound implications how confirming such a reality would not only revolutionize physics, but would fundamentally alter our understanding of our place in existence, challenging concepts of uniqueness, purpose, and the very nature of reality itself. The crucial thing to remember is that the absence of definitive proof is not a failure. It is the very nature of exploration at the frontier. This pursuit, this relentless questioning of the cosmos, is what expands the boundaries of human knowledge. It drives us to build better telescopes, to dream up more sensitive detectors, and to refine our theories with ever greater precision. The value lies as much in the questions we learn to ask as in the answers we might one day find. It is a testament to our species' insatiable curiosity, our refusal to accept that the story of existence is simple or fully told. We are compelled to look into the darkness and listen to the silence, not because we know what we will find, but because the act of searching is a fundamental part of who we are. Carl Sagan perfectly captured the spirit of this quest when he reflected, "The cosmos is within us, we are made of star stuff, we are a way for the universe to know itself." This search for echoes from other realities is the ultimate expression of that idea. We are the universe becoming conscious, turning its gaze inward and outward simultaneously, asking if there are other fragments of itself, other ways of being waiting to be discovered. It is a humbling and yet utterly empowering thought. Thank you so much for joining me on this incredible journey to the edge of science and speculation. This is a conversation that is just beginning, and I would love to hear your thoughts. What part of this cosmic mystery captures your imagination the most? Do you think we will ever find definitive evidence, or will the multiverse remain a beautiful, untestable idea? Share your questions, your theories, and your sense of wonder down in the comments below. Let's keep the exploration going.